Okay, let's get started. So in today's lecture, we're going to start with sequential logic. Now, for sequential logic, this is a relatively complex topic. So I plan to took 2 lectures to finish this topic. But if you consider this part, combinational logic, sequential logic plus Boolean algebra is pretty much a digital design undergraduate course for most of the universities, or at least most of universities in China. So I kind of feel we're rushing through a whole undergraduate course with 4 to 5 lectures. That's already pretty quick. Then what makes feel very different is that when I was an undergraduate student, it took me a whole semester to learn these things, and I spend so much effort and I still have something that I cannot solve. And this time, as I prepare this course, I feel, oh, it's probably only a few lectures time. So hopefully you can understand this concept, and that's a lot of topic, but we don't have a lot of practice. Hopefully later on, as we have assignments, you will have a chance to practice. So in today's lecture, we're going to talk about sequential logic. And sequential logic is on this other side of combinational logic. Remember last time we talked about combinational logic is basically a digital circuit that takes some certain input and always generates some other output. Now we typically consider the results are deterministic, and we almost immediately can get the result. At least we don't need multiple steps to get the final result. Then the capability of combinational logic is limited because you can only perform fixed functions. Then you always can predict the result. Then the result is very limited. It really depends on the combination of the pins, how many pins you have, then how many input pins, how many output pins you have. That's the your capability limited by the number of pins. But sequential logic, as you can see, that is a diagram for sequential logic. In sequential logic, combinational logic is still a main component of a sequential logic, but we start to have memory and feedback loops within this within the sequential logic circuit. Then the sequential logic circuit is still a digital circuit, and the output is not only depends on the input state, but also depends on the prior state, the memory from before. And the state update from the output of the combinational logic, so the state may change over time. So this is the sequential logic. It's getting more and more complex, but it's not too complex. In today's lecture, we're going to talk about how sequential logics are designed. Then for most of time, or input, one over input, you can consider input is going through the combinational logic circuit or going to the memory directly. So for most of the time, we're dealing with a clock signal and also a feedback signal that forms a loop. Now for clock signal, I think you must be very familiar with these terms of like Intel CPU works at 2 gigahertz, 3 gigahertz. Those are the frequency of clock signals. So that basically means in half a nanosecond or 1/3 of a nanosecond, the state updates once. The combinational logic will finish one set of calculation. That's why we're saying combinational logic is instantaneously, right, generated output. It's not perfectly generate the result in a moment, but it takes so short time that we can almost ignore execution time. Although eventually we'll see combinational logic circuit, the duration that we can calculate the result is kind of a limiting factor for how fast that our clocks can run. So as last time we were talking about building blocks for combinational logic. The building blocks for combinational logic are gates. Then the building blocks for sequential logics are still gates, but we're going towards one level up. We want it to be slightly more complex. It's a combination of a few gates connected in a special way. So we first talk about this type of logic component that is called latches. In combinational logic, we say every time we put an input, it will generate some output out, right? But you know, different gates may have different propagation time. The transistor close and open with different time. So there must be some transient state within the execution so that before you reach the final result, your output pins will generate some signals that is kind of considered as noise. Eventually, it will get stable and get you the correct result. But in the middle, it will give you some wrong result. So how can you determine which is the right result, or how can you determine what is the correct time? Right? We want to have something that called latches. Latches works in a way so that it will keep the signal, keep the output unchanged for almost unlimited amount of time until we want explicit, okay, at this moment, please change it, right? So it will prevent those noisy times. So the signal is jumping around. Then eventually we wait for a little bit until it arrives at a stable output. Then we say our latches comes in. So okay, let's update to the new state. Let's update to the new state. Then latches here. Then we keep the state, keep the state going. Then keep the output unchanged until we next round we generate some other result. Then we'll latches there for another cycle. So that is the purpose of a latch. Now it definitely comes from this type of like small component on a door that the door is latched when you don't want to open it. Then so latches are components that can code signals unchanged until we explicitly want it to change. So how latches are designed? Let's start with a very basic latch. So you may feel, if you see the combinational logic, you may feel this design is very weird, because in combinational logic, we typically consider the data flows from one direction to another direction. It never goes back. But starting from here, we have feedbacks, we have loops. Then typically, if you consider two NOT gates, two inverters, if two inverters are connected as a loop, if there are two inverters, then the data will keep flowing and going on a circle and keep going. Then the data that is stored inside it will never change. But if we only have two inverters, we basically have no way to change the internal content that is being latched within this inverter loop, right? So something similar to an inverter is a NOR gate. So here, there's our NOR gate. It's an OR gate with an inverter right after it, right? So we're using S and R signals to control the output. We call the output Q and Q prime, which should be always ideally should always be the other side of Q, not Q. Okay, so seeing this, you may feel it's very difficult to understand the logic of this thing. So let's draw a truth table and try to analyze what it's doing. So we start a truth table. Since these are OR gate, right? It's easy to understand that if one input is 1, then the OR gate is kind of connected. Then after a NOT, the result must be 0, right? So let me say again, this is an OR gate. If it's an OR gate, if any input is 1, the output will be 1, right? Then after the inverter, if any input is 1, the output must be 0. So let's look at the second row, or the third row. If R is 1, we don't really need to look at this path, right? We don't really need to look at this path. We only know R is 1. If R is 1, Q must be 0, right? So Q must be 0. Now if Q is 0, and S is also 0, the Q prime is 1. Right? Q is 0. Here is Q. Q is 0, S is 0, Q prime must be 1. So this solves the third rule. Right? So R is 1. If it's 1, this OR must also generate 1, but it's inverted, so it's 0. And Q is 0, S is 0, Q prime is 1. Right? So since this is a symmetrical circuit, then the second row and the third row are pretty much the same. So it's just flipped. Okay? The third row and second row are symmetrical. Then the fourth row is also easy to understand. If R is 1, this OR gate is connected, the result must be 0. If S is 1, this OR gate is also connected, then the result must be also 0. So Q and Q prime are both 0 in this case. Now you may say, oh, Q prime is designed to be not Q, right? How it can be 0, 0? So this is generally a state that we don't expect, we don't want this to happen. But if you really put 1, 1 in, then that is the result. The result is 0, 0. Okay? Then the hard part is the first row. If both are 0, what should be the output? Let's try to analyze it a little bit. Right? If R is 0, we don't know what's the state of this OR gate. It really determined on this Q prime. Right? If Q prime is 1, then this OR gate is connected, Q will be 0. Now if Q is 0, then this OR gate is not connected, the output will be 1. Right? So basically, is that if R is 0, we can only tell, so if R is 0, basically Q will equal to Q prime prime, right? Not Q, right? So Q equals to Q, basically. Right? So if you look at this one, we have two cases. If both R and S are 0, we have two cases. It's either Q is 0 or Q is 1. Right? Last time we were talking about when R is 0, then Q prime is 1, then this one is connected, then Q will be 0. Now if R is 0, Q prime is 1, Q prime is 0, then that will be 1. So what's happening is the current status of Q and Q prime is actually depends on the previous state of Q and Q prime. Right? The current status of Q and Q prime really depends on the previous state of Q and Q prime. And also, if the previous state of Q and Q prime is 0 and 1, the previous state is Q 0 and 1, then the current state is also 0 and 1. Right? Now similarly, if the previous state is 1, 0, the current state is also 1, 0. So we can write this truth table in this way. When R and S are 0, Q equals Q previous, Q prime equals to Q prime previous. Right? So which gives us two different modes. If we don't want the last row to happen, if R and S are 0, we say this is the latching mode. So if R and S are 0, we don't input any data, the output Q and Q prime will stay there, then will not change. Okay? If R and S are 0, Q and Q prime will stay there, will not change. But if R and S are 0 and 1, or 1 and 0, then basically whenever we set either one of them is 1, then we get the result to be 1, 0 and 0, 1. Okay, that explicitly set the result. Now we say either when S equals 1 or R equals 1, we said this is set mode or reset mode. Then that also explains why this thing is called SR latches. So because we need two input signals, one is the set signal, one is the reset signal. Whenever this set signal is 1, Q becomes 1, right? Whenever we reset it, Q becomes 0. So that is the logic here. So that's how latches can solve this problem so that the result won't change no matter what my inputs are, right? So set signal and reset signal. Any questions so far? So the problem of this design is S and R can be combined into one signal, right? Pretty much, they can either be all zero, or they can be. We probably only care about set. Reset is always negative, right? This is not very intuitive input that we have some requirement for the data to be in some way, to the input to be in some way. And we want to have another signal. Say, if this signal is 1, it's in set mode. If this signal is 0, we want it to be in hold mode, right? So that comes to another type of latch that are more convenient and easier to understand. And we call them D latches. What is D latch? D stands for data. Okay, so we first write the truth table. This is the truth table we have, and these are the building blocks that we have. We eventually want to implement this truth table with this particular building block. Now, what's the truth table? So we say when set signal is 0, we want it to be in hold mode. So don't care about the D. No matter what D we put in, we don't change the output, right? Now, whenever set 0 is 1, we're in the set mode. Then we set Q equals to D. Okay? Okay? Then how we can implement this logic with this component is basically we somehow need to convert a set and D signal into S and R signal. Now we know set and D signal, we know S and R signal, right? We have the truth table. We basically need to bridge these two truth tables together and use some combinational logic to somehow translate the set and D signal into R and S signal. Now you know how to design a combinational logic, so let's do a review for the previous lecture. So these D latches, we put R and S there, right? So when set is 0, R and S are 0. In this mode, we're holding the result. When set is 1, then or RS will start to have value. When D is 1, S is 1. When D is 0, R is 1. Okay, we reset when D is 0. When D is 0, yes. Okay, so we have the truth table. We consider this part as input and this part as output. So we need to create combinational logic here. And this combinational logic, right, so should be very easy. This combinational logic should be very easy. Last time we talked about this process that we need to first write down the equation, then draw the diagram, simplify the equation, and draw the diagram. So what's the equation? So remember the midterms, right? If the output has a 1, which is basically S has a 1, then we look at what's the condition that triggers this 1. It's basically 1 and 1. Set is 1, D and D is 1, then the result S is 1. In this case, we write down S is set multiplied by D, set and D, right? On the other side, R equals to set and D prime, set and not D. Okay, so those are the equations from last lecture. You should know how to write these equations. We can simply convert this equation into circuit that you can see is can be drawn in this way. Okay, two AND gate and a NOT gate. And we can convert SR latches with a more easier to understand, more intuitive D latches. For the set signal, we can simply replace it with the clock signal, so that on half of the time when the clock signal is 0, we set it into a latch mode. When the clock is 1, we allow new data to flow in. Okay, so what it looks like on a waveform. The waveform is something super annoying, but you still can read what is going on. So when the clock signal always works in this way. It has half of the cycles are low voltage and half of cycles are high voltage. This is a clock signal. Then the D signal, we just set up some random signals to try to encounter all the cases. Then we say when the clock, you should see the set is the clock signal. When the clock signal is 0, we are in hold period. In hold period, it basically means the Q value will not change. Let's assume it starts from high, then you can see during this hold period, the Q value will never change. Whatever it starts will stays there, right? Then on the other side, during the other half of the shifts, we call it transparent period. Transparent period means Q equals to D. So D changes, then Q will changes, as if they're connected through wires. Okay, so basically you can see it will go up and down, then here it will also go up and down, right? Here it's going up, then it's also going up. So for half of the duty cycles, the D latches will serve as a wire. For the other half, it will serve as a latches. You can almost consider it as a switch, right? It can be connected or disconnected. When it's disconnected, the result won't change. When it's connected, it's simply a wire. Okay, so these are latches. But latches still have problems. That is, so by the way, we typically draw the latches without the gates. We don't really care about the gates. And actually, if you consider CMOS level or transistor level optimization, it's actually not implemented without all those gates. It can be simplified with fewer transistors. So whenever we talk about latches, we just simply use this type of block signals. Transparent periods are something we do not desire, right? Remember, the problem with combinational logic is it takes some time for the data to converge until a stable state. Then anything that in the middle can fluctuate and generate some noise that we cannot tell if the result is useful or not. Then although we solved half of the duty cycles that is stable, but the other half is not stable. So we actually want to hold when both clock is 1 and clock equals to 0. Right? We want to hold it when both clock equals 1 and 0 so that we can get rid of this fluctuation throughout the life cycle, the duty cycles of this signal. How can we do that? If we can hold clock equals 0, we can hold clock equals 1 by simply adding another latch and a NOT signal, right? So we can do this. The first one, we call it a master. The master holds when the clock is 1, right? Because there's a inverter, there's a NOT gate. So it works as if it's just a regular latch. The second one also works as a regular latch. Then we can hold when both clock equals 1 and clock equals to 0. So then you can consider this as switches. When clock is 0, the first part is connected. The master latch works in the transparent style. So when clock equals 0, the signal D can flow to N. Right? When clock is 0, the signal from D can flow to N. No barrier, just as if it's connected with wire. Then when clock is 1, the signal can flow from N to Q, but not from D to N. Right? So this is something called a flip-flop. So it's either this side is disconnected or this side is disconnected. So this thing is called a flip-flop. And especially when these latches works in a clock signal, so they have a rhythm, right? They always do this flipping every half a cycle. And then for every 1 cycle, we have a open and close cycle. This is a flip-flop, and let's look at some waveforms and see what it is actually doing. Now we note some labels. The first label is D, the second label is N, the third one is Q. And D signal is still some random signal. We just put some random signal here. Let's look at N. Then N will have transparent period when the clock cycle is 1, right? D to N is transparent when the clock is 0. So it's transparent here, transparent here, transparent here, transparent here, transparent here, and transparent here, right? And it holds when clock is 0. Okay. On the other side, from N to Q, we can see it also has a transparent period and a holding period. The transparent period is this time, right? Yeah, the transparent period is this time, this time, this time, this time. Then you start to notice this feature that this is a perfect square wave. That means the value can only change at certain times. The value can only change at certain times. When it can change at certain times, it changes from from hold mode to transparent mode, right? Or from transparent mode to hold mode. So I always have difficulty understanding which part is his transparent time. This part is his transparent time. This is hold. Yeah, from hold to transparent, it always changes at this particular time. So it can only change at that particular time. I think the only problem here is only hard to understand part is this thing. Then if this one is turning from 0 to 1, but it's turning into a hold mode, so it doesn't really have time to let the signal to pass, so it won't change here. Okay, I know this is super hard to look at it, but spend a little time to check it and try to understand what is going on. And what we know here is on one part, on half of the duty cycles, when clock is low, our signal can flow from D to N, no problem, right? And on the other side, our signal can flow from N to Q at a certain time, right? So this causes an effect that even if you have difficulty understanding this waveform, you can just remember the conclusion here is that we can only change we can only change the result when our clock cycle or clock signal is going from 0 to 1. Now we'll call it only changes at the edges. Now when we are at the edges, for this moment, Q equals to D on rising edges. So at this moment, because Q is already passing, D is already passing data to N, so N has this value. And when we have a rising edge, suddenly the slave closes, then the N's data flows to Q. Then N is disconnected with D. So after that, no matter what D changes, the D's value will not flow to N and not to Q. So what is happening here is when we have a rising edge, Q equals to D for a short moment, right? After that, during the whole cycle, the Q value will stay there, will not change. Okay, so Q will follow D only on that moment. After that, during the cycle, Q will hold between the rising edges. Okay, so this determines that our digital circuit, sequential logic, when it has a clock signal, it always works in a way like tick, 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 in this way. So whenever we tick, what is happening is our signal from behind our register, or behind our flip-flop, can pass through this flip-flop. Okay, only at the time that we tick. Okay, so as you may notice, I'm saying behind the register, and flip-flop basically has another name that is called register. I think probably all of you heard the name register, right? Register in a digital circuit or in a computer is some circuit that can hold data. One register can hold 1 bit data. So we can write this D flip-flop as a simple form, this form, right? It's just a block with D and Q. Or even simple, sometimes we just write a symbol in this way. There's a clock signal, and there's an input and the output. The output always follow as the input when there's a rising edge or sometimes the down edge. So in some circuit, it will trigger by up edge. Rising edge sometimes will be triggered by down edge. It really depends on the hardware design. For the rest of the time, the result will hold. Okay. So if you look at this is a D latch, right? We need 2 D latches with 1 NOT gate to implement a register. So how many transistors are there in a register? So these are 1, 2, 3, 4, 5 gates, right? So 2 latches, that means 10 gates. 10 gates, so 11 gates, right? With a inverter is 11 gates. So remember last time we were saying 1 gate is typically considered about 4 transistors, like if all of them are implemented with NAND gate. So it takes 11 gates and 44 plus transistors to implement 1 register. But this is the result that we only consider at the gate level. However, in real scenario, if we can go down with transistor level optimization, we can reduce the transistor to something between this level. So there's no certain answer. It really depends on what's our goal. In extreme cases, we can reduce it down to a very few transistors. Like in the most extreme case, we can probably reduce down to 3 transistors. But that is a very special one. It's a DRAM style transistor. For most of the time, the smallest transistor without the reading and writing logic, we typically consider as 6 transistor. So 6 transistor is the minimum requirement to remember 1 bit in a circuit, okay, in a digital circuit. But if we're implementing a register in a core, like the register you write as R1, R2, typically requires at least 12 transistors, but sometimes can be more, up to 24 transistors. So just give you a feeling about the amount of data, amount of like die size that if we want to keep some data on our chip. Right? That's actually not a small number. To store 1 bit of data, it's actually a lot of overhead. Right? So come back to this design, then we have when we have a register or flip-flop, digital circuits can be simplified in this way, or can be represented in this way. A register, when it generates an output, it's connected with a combination logic. The CL represents combination logic, right? So consider the combination logic, although it's fast, it still takes some time, right? So consider we have a rising edge arrives at a certain time, then the Q will stay at a certain level. Q will stay there at a certain level, then we'll give some time for this combinational logic to do the calculation. Then remember last time we said the combinational logic, no matter how well designed, there's always some fluctuation eventually to establish a stable state. Then this fluctuation we can ignore because this output of this combinational logic will be hidden by this register, right? Will be hidden by this register. So this D's value, no matter what this D's value change, this Q will stay there as the previous cycle's value. This value will keep fluctuating until another rising edge arrives at this circuit, at this register. Whenever a rising edge arrives at this register, or result is already stabilized and already passed from the D to N part, right? Now when the rising edge arrives, then the N populates to Q and D equals to Q for that short moment, then Q will never change for the next cycle. Allows us for do more calculation here, then the D will get a new value. Still there are some fluctuations, some noises, but it will wait after a little bit of time, it will stabilize, so the data will pass through this register and put it to Q. Question?
Seems that if when you go to the D, when the circuit or the current goes to D, what if there's a small oscillation? It's supposed to be, for example, 1, but then just at that moment, what if there's a small oscillation with the number?
So, how do you guarantee? So I think your question is when there's a rising edge, how you can guarantee that this value is stable, right?
Yeah. The fluctuation is right at that moment.
So the quick answer is we should never have a fluctuation at the time that a rising edge arrives, because the fluctuation comes mainly from the delay of combinational logic, right? The fluctuation comes from the delay of a combinational logic. And if we can assume the combinational logic can arrive at a stable state after some time, then will be stable, then we can guarantee that the Q, let's say, if this is a rising edge, right? Then the D will spend some time to fluctuate, then it will become stable at the end, right? It will become stable at the end. At this time, another rising edge arrives, then it will fluctuate for a little while, then it will get stable, then another rising edge arrives, right? So it will only fluctuate at the beginning of this cycle, but not at the end. Are you okay with this assumption?
I won't give the right answer. is at the end, but what if we want at the beginning is 1, but at the end it fluctuates to 0? Now you guarantee at the right
Okay.
at the last moment, the number is correct.
Okay. So how can you guarantee that the computation is finished? Right?
I don't know if it's correct because when you come in, and it's supposed to be what you need is 1, but it's small fluctuation. When you reach the end, why do you think the fluctuation is still 1 instead of 0? Because if it's stable at 0, it's a wrong answer.
It's stable at 0 is a wrong answer. Now, how can it be stable at 0? Then there is something wrong with your combinational logic design.
Maybe we have to talk later because there's some confusion in my head.
Okay, so basically it takes some time to fluctuate, right, until it arrives at a stable state. Then with experiment with calculation, you know how long time it takes to finish one calculation. So for example, if you know one gate takes if one gate takes 0.1 nanosecond to finalize its open and close, then if you want to set 1 nanosecond as the clock frequency, you probably can only have 8 levels of gates, right? So that you have in 0.8 nanosecond, you can finish all the calculation. You still save 0.2 nanosecond for some safeguard to guarantee that the final voltage is being established at the end, right? If you need more than 8 level of gates, you have to split it into a multi-cycle operation. You cannot do that many things within one cycle. You have to make it a multi-level operation. That's why you probably heard in CPU cores, at the beginning there's probably 5-stage pipeline. Later on, it's extended to like more than 20 level pipeline stage. Why they do that? It's because they want the clock frequency to run faster and faster, but they probably have too much logic to finish. Then there's a trade-off. Do you have more stages, or do you want to have fewer stages, but each stage takes longer time, right? So this is something that is a design parameter that you need to say, if I want to run at the 1 gigahertz, I have to sacrifice the capability of each clock cycle. Okay, so if you still have confusion, let's talk later. Okay, so synchronous logic design. So there are some rules or some principles define synchronous logic design. So pretty much, if you say the strict definition for sequential logic, it doesn't have to be synchronous, but pretty much all sequential logics are synchronous. So you can consider this definition as almost as the definition of sequential logic. So every element is either a register or a combinational logic, right? So we have registers, we have combinational logic, and then at least the one circuit element is a register. So if it's a pure combinational logic, it's combinational logic. We don't call it synchronous logic design or sequential logic design. Then all registers have the same clock signal. We use one clock signal to control the whole chip. Although practically, even the clock signal propagation will take some time. It's very hard to guarantee pure synchronization. But if you consider localized clock signal synchronization, is not a big problem. Then every cyclic path, we can have cyclic paths. Then we can even have this combinational logic to generate a result that goes to the first set of registers. So don't treat this as a single register. It can be multiple registers here, okay? So every cyclic path contains at least one register, right? Then you cannot have cyclic path that is, say, one combinational logic, so you cannot go back to itself. Then this combinational logic is having feedback to itself, and it's not something that we're designing. Okay, it has to use register, serve in the middle. So registers, you can consider it in many different mental models, consider in different ways. So first of all, it's a gatekeeper. It will only allow the signal to pass through at certain rising edges. That's one thing. The second thing, you can consider it as a 1-bit memory. We memorize data for 1 bit, 1 register, 1 bit. So the combinational logic will take that bit as an input to generate some output, right? As 1-bit memory. Then you can also consider it as a separator, right? You do some logic, you temporarily hold it so that you will continue the work in the next cycle. And then in this combinational logic, so it's a signal holder. So many different ways that we can mentally model this register. And also starting from this point, I want to talk about the mental model of designing a circuit, digital circuit, a sequential logic circuit using combinational logic. Now, a combinational logic, as you can see from last time, is something relatively simple, right? It will take some input and generate some output. So for most of us, when we start to design a computer architecture system, computing system, we consider in a mental model, we work in this way. Let's say a cache. We receive a request. We first check if we have the data locally. If we don't have the data locally, we send the result to the bottom to another memory unit or another level of cache. Then we wait until the result comes back. And see my words. Then we wait for some cycles. Wait for the result to come back. When the result comes back, we store the data to local storage, and we also send the response to the top. So this is a very intuitive description about how cache works. But there's a mental model that we need to shift, is a combinational logic cannot wait. You give it some input, it will generate some output immediately. And it's like getting some work done, right? Then you will fall asleep. Then you wake up without any memory. You can only read what you have written in the piece of paper. And starting from that point, and you have a piece of paper that is your memory in the register. Then you have another task. Okay, take these 2 parts and do the next thing. Then you fall asleep and forget everything, right? Wake up, look at your notes, look at new task, do the task, then fall asleep. This is what combinational logic is doing. So it will never wait. So if you really, really want to wait, what you can do? You have memory, right? You put everything in your memory. You put everything in your note. You fall asleep so that when you wake up, you can still read your note to understand what happened before. So designing such a logic, sequential logic, is about to design the log that you want to write into a piece of paper and determine how you work on a task. How you work on a task when you read your note and take a new request and do the calculation and generate some output, right? So last time we talked about designing sequential combinational logic. And this time we're talking about designing the whole thing. So the register part and the combinational logic part. And how we design it is to basically use something called state machines. And state machine is a very strong mental model that can help us design sequential logic circuits. And I think state machine is something that kind of not only helped me understanding design circuits, then when I learned it, it also helped me like understand the word or change my own mental model to write even regular software. It changed me a lot. Then I hope you also can get to the point that why we can think things in another way. So let's use an example. This example is from our textbook. Let's design a traffic light. Now in this traffic light, we have two set of sensors, TA and TB are sensors. So sensors are something that detect if there's a cars there or not. Okay, let's assume this is super simple that it's not busy. Always only one car pass through this crossing. Okay. So we have two sensors. TA, we consider those are one sensor. Okay, although we have two sensors, but either one of them is triggered, then we consider TA is triggered. With TB on the other direction. You will also have light A and light B. Right? The light A, light B can be either red, green, or yellow. So here we have, that's the input and output. Then when you describe a system, before it describe what it does, always describe what's the input and output. And then always hear someone telling you, describe me, oh, I want to design a fancy system. And talk for 10 minutes, then eventually ask question, what's your input and what's your output? Then probably for many cases, it's actually very hard for them to define input and output. And it's actually very important to clearly define your problem to say, okay, here's my input and here's my output. Then using some mechanism, I can convert input into output. That's a way when you design a solution or a system. So this is a symbol that a block diagram that's for the system that we're developing. And we have TA, TB, LA, and LB. Okay. Then why there's a slash in LA and LB?
It's not digital.
Yeah. So it's 3 output is still digital. The 3 output, yes. So when we have 3 output, we cannot use 1 bit to control 3 lights, right? So that means it's a multi-bit wire. It's multiple wires, but combined together. How many bits it requires for LA and LB? 2 bits each, right? Because we only have 3 possibilities. Either 2 bits or 3 bits, right? If you consider how we can eventually control this thing, remember the 7 segments, 7-segment display. If we have three output, we can directly control them. Say 001 is red, 010 is green, 100 is yellow. That's one way to encode it. The other way is 00 is red, 01 is green, 10 is yellow. Then that's another way to encode our output. If using the second way, then eventually we need another decoder, 224 decoder, right? We need a 224 decoder at LA and LB to eventually drive 3 lights. But here, let's only consider case 2. We only arrive at the point of 000110. Okay, so let's list all the possible output. And the possible output are, let's say, start with LA, light A is red, light B is green. Now, if B wants to turn to red, want to flip, B has to stay for a little while as yellow state, right? Now it has to be in yellow state. Then after that, we flip actually to this state. The last state, LA turns from green and LB turns red. Then after that, if we want to turn again, LA has to go back to yellow, and eventually it can go back to the first state, right? There are 4 possibilities of light. It's impossible that both lights are in red, according to our definition. It's impossible both are red, both are green, both are yellow. There are many cases that we do not consider. We don't think they're possible. So with this possible output, we need to summarize them as state. What are state? In this case, we consider 4 different states. And to determine the state, sometimes this is a little bit complex, but for this case, it's rather simple. Later on, we'll see many examples about how we design this state and how we can design this state and how we can make useful circuit. But here, let's start with S0. In S0, state 0 is when LA is green, LB is red. Okay, this is our default state. Then to transit, if we want to flip, we have to let LA to go to yellow state for a while, then let LB stays in red. Then we can do the flip. Then in this case, LA is red, LB is green. Now, if we want to flip again, we have to make the S3, the fourth state. S3 is LA is red, LB is yellow. So 4 states in total that list all our possibilities. Now we draw these state transition diagrams with arrows. Then we need to say when S0 can go to S1. When S0 can go to S1, let's assume it's always triggered by a sensor. When a car waits there, then we make the change. So we call it not TA. So this is when we want LB to shift, right? That means there's no traffic going through TA. Then whenever there's no traffic going through TA, we transit from S to S1. If there's a condition in any arrow, we need to consider other conditions. So the S0 does not implicitly stay in S0 state, right? We have to have an arrow. So this is a special arrow that pointing to itself. It should be TA, not TA not. Okay, it should be TA. So when there's still traffic going through this academic avenue there, we want it to stay in S0. So light A is in green state, LB is in red form state. So we list all the possibilities. No matter what, we know what our next state is, right? Then we draw next circle. So this is an unconditional circle. So if it's red, if it turns yellow, after some time, it has to turn into flipped state. Then we draw the symmetrical line. So for TB, if there's no traffic, we convert to S3. If there's traffic, we stay in S2. And finally, turn the yellow. Eventually, a yellow light will turn red. So we go back to S0 state. So those are all the 4 states and how they transit. Yeah. Yeah. I know your concern. So yellow needs to take a few seconds, right? Green probably also needs some delay. Now, in real circuit design, yes, we do need to consider delay as a special type of like pointing back to itself for some time, right? But let's make it super simple. Let's consider we have a super long period at 5 seconds. Then you'll stay there for 5 seconds. Then 5 seconds later, we do a state transition. Okay, 5 seconds is a minimum time for state transition. That probably can solve your problem, right? Yeah. Some special state that no lights can change. Yeah, that can happen. I know your concern. So sometimes a counter is necessary, but here let's just make it simple. It's the beginning of a state machine. I don't even talk about clock cycle here. So those are state transition. Okay. So once we can draw this state transition diagram, we want to convert it into a state transition table. So this table basically describes current state, input, and the next state. For every arrow, we need to write one line here. So for example, if our current state is S0, and when TA is 1, we stay at S0, right? That's the self-pointing arrow on the top. And when S0 is 0, as TA is 0, we flip, we go to S1. For S1, we don't care about input, we always go to S2. For S2, And it's the same thing. Then we go to stay as S2 or go to S3. Now, when at S3, we don't care about the input. We always go back to S0. Right? This is a state transition diagram. And we make these transitions. It's all the possible transitions that we describe in this table. This is really a small example. The real problem can be much more complex, but that's our starting point. Okay, so next task is we want to consider state and output encoding. So we want to encode the state and output. We want to represent the state and output with binaries. So how many bits it requires to encode the state? And it's always a 2 to the power of n problem. If we have 4 states, we need 2 bits. Right? If we have 5 states, we need 3 bits. Then, although we wasted three more states, but that's the only thing we can do. If we're more than 4, we need 3 states. If we're 8, if we have 9 states, we need to have 4 bits to represent the state. Okay, so for output, we already talked about we use 0, 0 to represent green, 0, 1 to represent yellow, and 1, 0 to represent red. So then we can convert this state transition table using bits rather than symbols, S1, S0, those symbols. We can write into this thing. Okay, then here we have the input part, right? These four bits are input, and these 4 bits are output. This 4-bit state and current state and input are the input. The next state and output are the output. So 4 input, 4 output with a design of combinational logic is something that we covered in the previous lecture. Right? So let's keep going. We don't really have to design a big combinational logic circuit that considers 4 input and 4 output. We can combine into 2 parts. One part is from the current. One part is using this 4-bit as input to calculate the next stage, right? Next state. So this next state combinational logic. Then you can use a kernel map, right? Or you can just looking at the result and try to simplify it. Now for this case, it's rather simple. We can just go ahead and simplify it. So here, let's look at Sn0. Okay, Sn0 is, this is Sn1, this is Sn0, and current state is S. SA0, how many ones we have? I have 2 ones, right? 2 ones here, so we have 2 minterm. And then look at the input, we have S1 prime, S0 prime, and TA prime, right? If there's 0, when we set it, we write it as not state. Now here, for this term, we write it S1, no prime, S0 prime, TB prime. For X, we don't care about it. Okay, that's the way we write Sn0. Now for Sn1, it's a little bit more complex, and we consider this case. For this term, we have S1 prime, S0. Right? Now for this case, we have S1, S0 prime, TB. For this term, we have S1, S0 prime, and TB prime. Okay, just use all the ones to generate every minterm in this sum of product form. Now, this is sum of product form. It's not a minimized form. So we can simplify it. How we can simplify it? You can probably it's very easy to check to find that this TB and TB prime can be taken out and can be cancelled, right? We have done this a lot last time. So it's basically S1, S prime 0. So we get this. So TB doesn't matter at all. TA and TB doesn't matter at all for SN1. Then, see, are you familiar with this representation? Yeah. Remember, every time we say, if it's only 2 input, we can probably generate output. We can generate output with 1 gate. So in this case, this is XOR again. Okay? So SN1 is S1, S0 XOR. If they're different, the output is 1. If they're the same, the output is 0. Well, you don't need to ask why this happens. There's no fundamental reason. It's just a coincidence. Okay? It happens can be represented by an XOR gate. For SN0, basically we have no way to simplify it. Okay? Now on the other side, we look at the output combinational logic. So the output is only related to the current state. If we have a current state, then we can generate the output. Right? So the current state, this is how we design the system. We say our current state, we first list all the possible combinations of output. Then we define the state. So of course the output is tied to the current state. Okay. So in this case, it's also easy to write this 4-bit output, right? So I won't really explain how it's derived, but it's super simple. Okay, it's because there are only 2-bit input. Okay, so at this stage, let's give a quick overview how we arrive at this stage. We have the problem, we have the symbol, we define the input and output, we list all the possible combination of output. Then we consider each possible output as one state, right? We define the state, there are 4 states. Now we summarize how this state can flow from one state to another. What's the principle? What input triggers state transition? Then we write down this state transition table. We convert these symbols of state into binary representations of this state, state transition, right? Then using this state transition with 4 input and 4 output, 4 input and 6 output, we can generate equations. We can generate 4 Boolean expressions that describes what our circuit will be if we want to design a logic like this. So once you have this style, once you have this expression, then it's not hard to draw a circuit. So let's draw this circuit together. Then I wanted to split into 2 slides, but it appeared at once. That's okay. Let's explain a little by little. So we start by a register. Okay, a register stays there. Then this register have S1 and S0 as the current state, as the current output, right? And Sn is the next state. No, remember, no matter what we change the next state will only become current state when the clock signal is a rising edge, right? So it will pass this barrier, go past this mountain only after we see a rising signal. Okay, then the signal will start to generate and we'll loop back. This is a feedback loop. You can see there's 2 parts, right? This is S0, the inner circle is S0, the outer circle is S1. So we're definitely writing a simplified style of a circuit because we'll have a 3 input gate and with inverters directly represented by circles on the input side. But you understand what's going on here, right? So these are the circuit that express those expressions, implement those expressions, right? So it will take some time, go back to this place and calculate the next state's value. Now, only the rising clock arrives, the rising edge arrives, will pass this barrier, then Sn becomes S. Right? Then we start to calculate next round. At the same time, on this side, we call this group of circuits the output combinational logic. So the output combinational logic only depends on S1 and S0. And using 3 very simple gates, we can generate 4 output bits. And these 4 output bits can drive the lights, red, green, and yellow lights to turn on and off. Okay. So this is a very simple example of how we're converting a problem into state and eventually into a circuit that implement this logic. Then it's a little bit oversimplified. For example, we didn't say how long the clock cycle is and how exactly the sensor works. But this is the first example that I can show, the whole process, that how we can arrive at this point. Then in the next lecture, I'm trying to give you more concrete examples, like the more building blocks of digital circuits for both combinational circuits and sequential logic circuits that can eventually build very complex computing cores. So, okay, a summary for today's lecture. Then we talk about sequential logic building blocks. We talk about latches and flip-flops. Then something that you can forget, something you cannot forget. Something you can forget is how the latches circuit is drawn, how many gates are there, what exact gates are there, then how to analyze like the cycles of signals. Eventually, just remember one thing. Flip-flop is a register, and Q equals D when we see a rising edge. Then Q will hold at this value until next rising edge. Then next rising edge, Q will equal to D again. So D will pass that register whenever there's a rising edge. Then it will not change the output no matter D changes after the rising edge arrives. Then we talk about state machine. We use a concrete example to describe how we can convert a problem into state machines, then eventually design digital circuit, sequential logic circuit, and especially in a synchronized digital circuit style. Okay, I think that's all for today's lecture. And let's talk again on Thursday.